thank you to Aaron and Kara May, wherever you are, for all the heavy lifting on organizing this. I know it's often a logistical nightmare to put these things together, and it's come off incredibly smoothly. So I know that that doesn't happen without a lot of hard work. So thank you. So aquaculture. For those who kind of tuned in last week, I didn't give much of a brief in terms of where all this work is coming from. By training, I'm a molecular and population ecologist, and spent most of my graduate years and early part of my academic career, dealing, and still do, actually there's a whole other research program that we're not going to talk anything about, that's field-based, and we spent most of our time, and continue to spend a lot of our time, on the issues around aquaculture, the ecological issues. Notably, recently, we've wrapped up a number of your studies on sea lice. We continue on with escapes, pollution of various forms, et cetera, et cetera. And it became increasingly frustrating and challenging as an ecologist, recognizing that while the amount of information continued to build, pointing, you would think, any dispassionate decision maker towards a particular direction, no action based on science was ever taken, and now, frankly, I don't expect a whole lot of sort of science-based direction to occur. And well, how do we break this logjam? How do we start to better understand what the issues are and actually provide policy relevant information? And I began to think, the classical triple bottom line, and how do we line up all of those things in the context of aquaculture? And I realized the first thing that needed to be done, and surprisingly hadn't been done up until that point, it was a baseline of aquaculture performance, and this is what led to this GAPI idea that you guys, I believe, have read a little bit about, the Global Aquaculture Performance Index. It was this initiative to try and put a baseline of performance of the global marine finfish production, and allow us to start talking apples and apples, oranges and oranges, outside of this species produced in this place, and kind of encapsulate the discussion that way. This is not, this work did not happen in a vacuum at UVic. It required a number of people. We had expert workshops conducted throughout North America on particular issues, and how do we deal with, or how do we measure impacts of parasites and diseases, for example? Not a particularly simple or straightforward exercise. And what's more, GAPI is the aquaculture, mariculture specific application of EPI, which was born here, the Environmental Performance Index, with colleagues at Columbia University. And so this is something of a homecoming for GAPI, back to its academic homeland. And so what we did was took what I found to be a really engaging and powerful analytical foundation, and then apply it and tweak the tool somewhat, and apply it in a mariculture context. And so that's what we've done. So to give a little bit more background on this and why we did it, we're aiming at North American and Western European markets. And granted, when you look at this breakout, marine finfish aquaculture doesn't represent a large proportion of global aquaculture activity, but in terms of the markets that we seek to affect, North America, Western Europe, marine aquaculture products do play a dominant role in those marketplaces. And so we thought that this was a reasonable place to start. How do we decide what species are included and what species are not? We said we want to include all of the species necessary to capture 90% or more of the global production. Right? So that equaled out to be 20 species. And then how many countries then do we include within it? So if a species is produced in 20 countries, then do we need to assess that species in 20 countries? No. How many countries do we need to capture 90% of the production of that species? Okay, so we have two decision rules for inclusion. And what's more, we wanted to focus on outcomes, on actual performance on the water, which was something of a novel perspective, and to this day actually remains somewhat novel, as opposed to theoretical, best case scenarios, best practices, qualitative, aspirational kind of goals, all very well and good, but we wanted to know what's going on the water today. And we used the proximity to target methodology, which we'll briefly touch on in a moment. So to then actually do the assessments, we had a number of other decision rules that we wanted to keep to. Obviously, the indicators that we were going to use had to be relevant. They had to actually be directly attributable to environmental sustainability. Like I already said, they have to be performance-oriented, not aspirational or qualitative or something. They have to actually be measurable. Transparency, whenever you're doing anything that has winners and losers, potentially, transparency is absolutely fundamental. Otherwise, you will very quickly be engaged in firefights one way or another. And so everything we've done is and continues to be transparent. All raw data all the way through, all the analyses are available on the web. And this also is really important too, because as soon as we started generating results and the losers quite predictably said, oh, damn it, you've got it all wrong. I said, well, maybe we do. Here's our data, here's our analysis. Show us, what have we missed? And in a couple of cases, we actually did. There were mistakes. And we gained a certain amount of credibility in the eyes of those who were done wrong by saying, absolutely, we'll correct it, and did everything we could to try and make it right. The majority of time, though, the conversation ended there. And that was the last we heard of it, except in the case of a couple of supermarkets who still want to sue us, but we'll get to that in a minute. And data quality goes without saying. We need everybody needs the best quality data one can find. And so we engaged in a pilot project, and we went out and said, okay, here are sort of our coarse-grained issues of how we're gonna assess this. What do we actually assess? And we did a pilot project where we went out and looked at 36 of the major sustainable seafood initiatives out there, and asked what are the issues that all these different various organizations, buyer guides, et cetera, are looking at. And a set of indicators popped up again and again and again, and those were the ones that we decided to go with. They had passed something of a peer review by virtue of the fact of showing up, again and again and again, like escapes. Right? No matter whose buyer guide or what you look at, escapes is always an issue when it comes to aquaculture. So therefore, okay, escapes has to be included here. So when we did all that, we came up with these 10 indicators. And come on in. No, gone. We ended up with these 10 indicators, and I don't think any of them are particular surprises. We broke them out into sort of functional groups, inputs, discharges or outputs, and then those things that once released continue to grow, evolve, change, become a moving target. So, of course, you could conceivably measure hundreds of things. If you look at the WWF buyer's guides or standards program that they're coming out with now, literally for salmon, there's 127 different items that anybody who wants to get that logo on their product needs to meet. This, in some eyes, is perhaps a little over the top. We decided, we could measure 100 different things if we wanted, but these are the 10 core elements. And so something like a Zagat's guide or a consumer's reports where I don't need to know everything about it. I'm looking for the key things that are going to separate the better products from the worst products. Keeping it simple. So that's essentially what we've done. You've seen the document. You've seen this, particularly complicated set of equations. We don't need to go into it, though we can if you're interested. There's a tremendous amount of sort of heavy lifting embedded in this to get the data together and then do the analysis. And come to some kind of conclusion. And then, how do we conclude is also another kind of sticky point. We have a range of environmental performances that we could measure against. And we have a line, or we didn't want to get into the situation of defining a particular line, and we're not a standard, right? Some standards, they set the bar quite high, others set it quite low. And we wanted to say, you know what, we're not interested in pointing to you're sustainable, you're not. We're trying to develop a tool that is separating out the players in a pool of players and say, who's better than the others? And so we're setting a admittedly impossible goalpost of zero impact. And it doesn't matter that no product in the world no manufactured product anyway, can meet this goalpost. That doesn't matter. It is an invariant, no matter how technology improves and how efficient things get and all the rest of it, zero impact will never be met. So therefore, it will always be a goalpost against which we can measure. And we're simply asking, how far is the product from that particular goalpost? Right, and so we've got here a couple of salmon products, and the Norwegian product score 72. It's slightly closer to that zero impact than the Chilean product. And that's interesting in and of itself, but because we have a standard set of metrics and applications, we can begin making cross-species comparisons. So in this case, we've got amberjack, Chinese and Japanese product. Looking at the comparison within this species, why is the Japanese product scoring better than the Chinese product, right? That's sort of a policy relevant point right there. But even more interesting, and the real novel application of this, is we've now got a tool that we can compare apples and apples, oranges and oranges, across two different species grown, well, in many parts of the world under, in some cases, quite different types of condition. And we can, on the same playing field, make a determination around the relative performance of these various products. The leading, or the number one top performer was Chinook salmon coming out of New Zealand. And this spider diagram you see on the left depicts the performance in each of those issue categories. The grayed in area in the center represents the average performance of all products in the world. And then the blue line traces the plot for New Zealand salmon. And so the score of 73 is the area encapsulated by that blue line. Now you can get to 73 by almost innumerable combinations of moving that line around, right, covering the same area. And so what's particularly interesting here is it points out where things are really good and where there is opportunity for change. For example, in feed, you can see it meets about the global average for all species. And that is a reflection of Chinook salmon, particularly in the New Zealand market, being relatively new product, only being a few generations removed from wild stock, and therefore has not been gone through the number of generations of selective breeding to optimize feed conversion ratios and so forth. So if we looked at Atlantic salmon on the same plot, you'd see a better score there, but worse in other areas. And then we compare, now we've got a Chilean product of Chinook salmon to compare, and we can see why New Zealand sits out on top relative to Chile. And we can make comparisons against the other species, which sits at the bottom of the ranking, the bottom of the class, which is grouper. And even so, no matter where you grow grouper, it's a bit of a nightmare. You can see even within the grouper category, there is some quite variable performance.
Is the grade global average?
Yes. Yeah. So just to show where that particular product lay in reference to a global mean. Okay, so a grouper is not a grouper. So for the first time, we can start teasing out, for example, for Indonesian grouper, BOD, biological oxygen demand, or organic pollution, is a much bigger problem in Indonesia than it is for the other areas. And so if we have limited resources that we can apply to trying to get Indonesian grouper production up to some sort of standard level, then BOD might be an area where, you know, it's a low-hanging fruit. We can make some achievable gains quite quickly simply by looking at other jurisdictions and copying what they're doing. And so we've got our indicators. We generate a species country score. What I've discussed so far is the normalized score, and that is the performance per metric ton. We very quickly realized that score, though, is ecologically irrelevant, because the ecology of the receiving environment, or the ecology period, doesn't matter, doesn't respond to the performance per metric ton. It only responds to the cumulative performance, or the cumulative production. And so we generated another set of scores, which was the cumulative species country scores, and broke them out in terms of species and country. So when you start flipping through that document, you're basically awash in scores, and I appreciate the fact that it can be challenging to follow something through from beginning to end, knowing that we've got 4 different flavors of scores coming out the other end. But from an ecological point of view, or sustainability point of view, it actually makes a surprising amount of difference. And so here's the sort of one of the busy results of that. Remembering that we're on a 0 to 100 scale, so the taller the bar, the better. Normalized score in red, cumulative score in green, and then the squares, the little orange squares, represent the production assessed. So a couple of things jump out at you pretty quick. We have numerous examples where we've got very high normalized scores, but are countered with very low cumulative scores. Right, so Norway being kind of the textbook example, their Atlantic salmon and Norwegian production is dominated almost entirely. There's some cod and a couple other species in there, but it's mostly Atlantic salmon. Score 72 on average, but dropped to 34 as a result, driven largely by that square way up at the top, which denotes a tremendously large production. And then we can contrast that with Australia and France that tend to be characterized by growing really problematic species. These are from an ecological point of view, these are tremendously expensive species, but because their production is so small, their cumulative score actually rises to the top. So the take-home message here is that, you know, it doesn't matter how bad a farm is. I mean, you can have the worst farm in the world. If there's just one of them, the total ecological impact is rather modest, as opposed to you can have really highly efficient farms, but if you've got thousands of them, like they do in Norway, right, that's a problem, potentially. All right, we can also rank them according to species, so in descending normalized, or sorry, cumulative, no, what have we got here? See, I even get mixed up. Descending normalized scores. So, surprisingly, you know, the salmons sit out up here. Right? If you go to BC, you know, Atlantic salmon are right next to, you know, the devil in terms of impact. Right? And so we caught a fair bit of flack from our friends in the NGO community by giving what they saw as a free pass to salmon. And, you know, as I need not explain to you, you know, there's very little black and white in any of these stories, and the real interesting parts are in the gray, and this is no exception. And so, if we take those scores and then plot them, scores per metric ton, total production score, cumulative impact scores, we get this array of players. And down in the bottom here, we've got So these are the players who score poorly per metric ton and poorly cumulative. These are the worst of the worst, and they tend to be the youngest industries. So the colors actually represent the age of the industry, or the number of years that these products have been in production in these countries. And aquaculture is a trial and error kind of activity, like many industries, particularly in the early phases. And error actually manifests as ecological impact. The intermediate, where we've got the intermediate age and also intermediate scores. And then, interestingly, when we get down to these guys, so we've got high per ton scores, but low cumulative scores. Atlantic salmon being here, milkfish in Indonesia, a few others. Right? These are the ones that have actually grown in response to becoming efficient. This is what I was getting at last week in that lecture, this double-edged nature of efficiencies, that it's because of this high score actually drives down or provides economic incentive to engage in more and more production of these things, and then that drives down the cumulative score. And then finally, the fastest growing ones also happen to be the most problematic. And so that, in a nutshell, is where we ended up with the GAPI program. We then had so we had this baseline of performance around the world. And it became, not surprisingly, obvious that this is a really complicated issue. And we research it, we live this stuff, and our head is spilling. So imagine what it's like trying to be a consumer who walks into the supermarket and says, I'm trying to buy something that I can look in the mirror, after I eat it, and not be disgusted with myself. And so as a result, what I call the sustainable seafood industry has arisen with great vigor. And all of these things are the labels, a lot of them consumer-facing, that are geared to try and remove the difficult calculus out of trying to buy sustainable seafood for dinner. And we started looking at it and wondered, well, we've got this baseline of conventional production. I wonder what it would look like if we started assessing these products produced under the constraints that one would have to meet to achieve one of these labels. Right? And so this is another product that we produced. How green is our eco-label? And we asked a fairly simple question. What is the minimum environmental performance required to meet one of these certification levels? And so you can imagine, here's our GAPI score, 0 to 100. Imagine some theoretical product that scores 70 normally. And then under some label, be it organic label, an industry label, some kind of sustainability label, its score rises to 81. And so it has a value added of 11 points. Right? And so 11 is our metric. That's the value of the label. Here we have our series of labels, and they're ordered from highest performing to lowest performing in absolute terms. And up at the very top is the U.S. National Organic Standard for salmon. It is so far a draft standard, hasn't been enacted, and the industry has come back and said quite strongly that it is a standard that cannot be achieved. I guess we'll wait and see. Things get really interesting when we start looking at, okay, there's the absolute values, but what do they represent in terms of value added to the products they seek to endorse? And so, not surprising, the U.S. National Organic Standard sits up top, representing 21 points above the average product, and again, it's dominated mostly by salmon. We've got a couple other interesting. Australia Organic sets a pretty high value added, mostly because Australia is dominated by such terrible species, right, that any step in an ecologically minded way is going to result in a significant improvement over what is largely a deeply problematic mariculture industry. With the exception of those couple at the top, we get very, very modest return, sitting usually 1-2 points. Statistically, I would venture these are not statistically different from zero. In fact, we have quite a number of zeros, and then we have, so Marks and Spencer's, actually their label, their store label, set a bar 10 points below average production for, this is salmon, average net pen production of salmon. Hence the lawsuit. This got picked up by The Guardian. The Guardian just bled it for everything it was worth. It was one of those cases where, here's our data, show us, please, where we went wrong. No, we'd rather just, make this into a bit of a gong show in the courts. So I'm pretty sure this is all going to blow over, but there you go. So when you start thinking about how much effort and money, time, capital has gone into all of these labels, and think about what kind of return have we gotten as consumers, have they gotten in terms of trying to meet their mandate of presumably trying to affect positive change? This is a huge wake-up call. The five leading labels are organic labels. There might be some informative value there. By and large, we're looking at less than a 10% gain, usually quite a bit less than 10%. Organic labels tend to be more so than others ideologically driven. And so they tend not to be focused more on, how easy is it to adapt to this? How easy is it to meet these standards? Whereas the industry-driven labels tend to be a little bit more adoptable, if that's a word. But it does, being more adoptable also, means by and large setting the bar lower. And that brings up an interesting kind of question. Is it preferable, if you're trying to affect positive change, is it preferable to set a more modest bar that will have greater buy-in from the industry? Or is it preferable to set a higher bar knowing that you're only going to be able to certify a small section of the industry, but hope that creates either the carrot or the stick, I guess, depending on how you look at it, to bring the rest of it up? And this debate is ongoing within the sustainable seafood world as we speak, and I don't see it being resolved categorically one way or the other. But it does present a bit of a problem. And then interesting, we were only able to find, as much as Marks and Spencer's and Whole Foods is up there. They're the only two retailer. There's plenty of retailer labels out there, but we were not able to find any, with the exception of these two, that actually had any kind of metrics associated with them. We're going to do good. We're going to try our best. This is literally the kind of thing that is characterized a lot of these labels. So when we started out with 36 of these labels, we started out with 36 to kind of set the groundwork for, the peer review for GAPI, what should we include in the GAPI, but then we also came back and reassessed them for the purposes of this benchmarking. We started out with 36, but only 20 of them actually had anything we could work with, right? The other 16 were vapor standards. There some, that we looked at had a web page. There was a web page, and that's all there was. But they did have labels on product in stores. It was eye-opening. Right? And so a couple of things fall out from this. the fact that we could only actually measure something interesting with a little over half of these labels was telling in and of itself. The market is rife with lots of what I would call greenwashing, simply because there's an economic incentive to do it. The fact that the vast majority of these kinds of initiatives, the labels deal in qualitative or best practices kinds of objectives, presents a problem in terms of how do you actually assess if you're gaining anything, if this is yielding any kind of net positive movement. And this is something I just keep coming back to because I think it's just the elephant in the room is the issue of scale. Right, and as I think this was included last week, we've got this situation where Norway scores 72 on a per metric ton. That's because Atlantic salmon is an old industry. They've kind of worked out a lot of the bugs. They've started producing a product that can be done relatively efficiently, which is to say you can produce a good amount of product for a relatively modest amount of input. That doesn't have anything to do with the ecological performance. But when we start looking at the scale of production in Norway and the impact that production has on the coast, that's a pretty big problem. And I don't know, did that slide come out last year? Yeah. I mean, what's going on in China is just astounding. And it really makes a little difference if we start cherry picking this farm, that farm, or start looking at per metric ton performances when you've got this scale of activity going on. We definitely need to be jettisoning the per metric ton criteria and looking at it from a cumulative standpoint. So up until this point, so in this part of our story, it's a pretty dire situation that we've got an overall performance, even the top performing products in the global aquaculture, at least mariculture world, are sitting at a C, right? That's the top of the class is getting a C grade. And then it gets progressively worse from there, which generates a lot of angst on the part of consumers. And so we have this sustainable seafood industry pop up with all of their labels, the majority of which mean very little. What are we going to do? Well, there's a lot of technological advances going on in this world. We've got integrated multi-trophic aquaculture up in the top left there. And I'm sure most of you are aware this is where we have the target species being grown above other potentially harvestable species that consume the byproducts of your target species. We have solid walled, so typically floating, not cages, not open net pens, but solid walled enclosures where we can grow our fish. We have flow-through systems, and we have so-called RAS, or recirculating aquaculture systems. And these are these are all in various stages of development, some much further ahead than others, and are very quietly sort of reshaping the entire aquaculture world. And this is Val Etier. She's a graduate student. Well, she's almost not a graduate student anymore. She's just on the verge of defending her work and is actually an ex-Princeton rower. But we'll talk about her work here anyway. And she's looking at the farm level assessment of these technologies. So this has the unfortunate name of Flappy, which was based on GAPI, which was based on EPI. So this is the grandchild, perhaps, of EPI, great-grandchild of EPI. And so Val's work is taking the GAPI framework, tweaking it again, rather than looking at species and country, but now looking at it at the farm level. And in the intervening time that Flappy was released, Monterey Bay Aquarium, which is the Seafood Watch program, which is, I think, well, it's not even arguably, it is the leading brand within the sustainable seafood world, took GAPI and then retooled their whole assessment package that is now on a 100-point scale, and it's performance oriented, and it has all of the same kinds of indicators that we're looking at. And so it's been gappy-ized. And so what Val's done is taken the MBA tool and then we think made some improvements to it, which we're going to hopefully talk them into adopting. But in the meantime, use this new farm level tool to assess those technologies. And in the same way that we did with the label benchmarking, we're now saying, what kind of value added are we looking at if we produce product, and particularly salmon, because this is where most of the world is focused on in this part of the world. Growing salmon in these different technologies, what can we expect to achieve using these technologies? And so here's our old spider diagram again. And we've got, so again, to reacquaint you with the names, the Recirculating Aquaculture Systems, IMTA, Integrated Multitrophic, so the not polyculture, but an integrated multitrophic aquaculture system. Open net pens, so conventional open net pens in the green, then flow through and solid side. And we did some statistical analyses and said, well, geez, some of those lines look like they're following very similar paths. Statistically speaking, these don't look like they're all independent of each other in terms of their performance. And, turns out they're not. That IMTA, the multitrophic, and conventional net pens, almost no difference. Right? And you can follow those two lines around and see it. The only difference is a slight bump in improvement for IMTA and effluent. So too for the flow through and the solid sided, very similar in terms of performance and statistically not differentiatable. And so when we collapse them down, we get a slightly more digestible series of plots where we've got the net pen IMTA in red, solid and flow through in green, and then RAS by itself, clearly the standout performer. Where things really kind of collapse down on top of each other, though, is feed. And a couple other spots too, and we'll get into that. But I wanted to focus on this RAS, or recirculating aquaculture. We can talk. I know you're interested in IMTA, and we can talk about that. But so far RAS is kind of the potential real star that isn't gotten a lot of attention yet, so I thought it was worth kind of going into it a little bit. These are recirculating systems that are absolutely closed, right? So they're 100% biosecure, right? We are done with diseases and parasite transfers to wild systems. Because they're biosecure, we've also eliminated the need for the vast majority of antibiotics, parasiticides, obviously antifoulants, all the nasty chemicals. There's farms now operating that are 100% recirculation. So in other words, when the fish are harvested at the end of the production cycle, they're removed from the same water they started that production cycle in a year, 14 months earlier. It's a huge technological advancement. Because the system, the environment in which these fish are kept, is so tightly monitored, you can have densities that are about 7 times higher than conventional net pens. Not only can you have, in fact, the fish respond better. And there's a growing amount of literature that is documenting this, that when looking at stress hormones, cortisol, et cetera, in these fish, the level of these indicator physiological chemicals are actually superior in the flow-through, or not the flow-through, in the RAS systems than in conventional net pens. Up to 100% water circulation. So removing the requirement or the externality of water in the equation. So in conventional net pens, yes, they're sitting in the water, but the whole business model is predicated upon lots of current moving in fresh, oxygenated, and in the case of salmon, cold water, and then moving out oxygen depleted, nutrient-rich water out of that system. And then all of the sort of allied issues that go along with it. In a particular system that is running, and this is one of these 100% recirc systems in Nova Scotia, Canada, the effluent, because there's no chemicals involved in the entire production cycle, the effluent, the organic output of this farm is meets all the organic standards out there and is trucked down the road, literally just down the road, to an organic farm. And sold. So there's actually additional value streams that are available to this this kind of production that might not be available to other forms. Again, because the environment is tightly controlled at an absolute and invariant optima, the growth cycle is decreased. So you can move more product through your farm per unit time than you would be able to do in an open net pen situation. And because it's a completely closed system and can be taken literally anywhere, but with salmon, there are systems now that have grown salmon in completely fresh. You don't need salt water to grow salmon. In brackish, so a mix of both, and then complete marine. And so therefore that opens up the possibility, or it's a pilot study proving that this type of system should be amenable to any of the 400 plus species that are currently produced in aquaculture systems. And this is potentially the most exciting aspect of this set of technology, or technologies that form RAS, is that no longer is this necessarily the context of a salmon farm. At least, in British Columbia, where this photo was taken, out in the middle of nowhere. You can now take the production of the fish and move them into, if not the center of urban zones, at least on the periphery of urban zones where the fish are going to be consumed. Because when we're talking about embedded energy, and this is always the knock against RAS and to a certain extent these solid-sided systems, is that they're much more energy intensive. Fair enough. But by far and away, get my numbers right, 94% of the embedded energy in the typical salmon product is in its transportation, not in its production. And so while yes, and we can go back to those spider diagrams and look at energy again, yes, these RAS systems do have a higher energy requirement because you're now looking at 7 times the density and you're removing 94%, well, if you're bringing them close to where they're going to be consumed, up to 94% of the embedded energy, the total energy equation drops precipitously down. And it gets them out of my coast, which I like the most. Yeah?
I completely think that's an awesome prospect, but there's a big difference between the relative water quality in both of those localities. So the water quality is very pristine, the previous picture you showed from British Columbia.
Oops.
However, in a city where the water is already highly compromised, the impacts of that type of fishery will be quite different.
This water is anything but pristine.
Okay.
But I don't think we're talking about 2 different kinds of pristine. This water is full of pathogens, it's full of disease, it's full of wild salmon, it's full of potentially noxious chemicals, although in this particular context probably not. It could be though. When we're talking about these RAS systems, I think we need to separate the RAS system from a lot of these other land-based systems which are not recirc systems. Having a recirc system means that you are controlling to a very fine degree all parameters of water quality. So even if you're starting with water that a human can drink, which I think is a fair assumption, your water quality is going to be superior in the case of raising fish than anything you're going to get sort of ambient water in the marine environment. What makes the RAS technology viable is that it maintains that quality through the production cycle. And this is not a trivial technical consideration. This is state-of-the-art water quality science that's going on. The point, though, and which I'll get to in a moment, is that it's matured to the point where we can now, well, not we can, they are producing product, bringing it to market for for only a small fraction increase over conventionally produced product. But because you're removing the cost of transport, or potentially so, right, the actual economics then switch into favor of the system. So I don't think, when you say it's not pristine, I just want to make sure I'm answering the question. When you say, what are you thinking of particularly?
I guess what the new systems will be non-integrated into these water bodies. They'll be independent of.
You fill them up and you're done. And then they drain with each cohort moving. So you bring a cohort to market, drain, fill. That's what I mean. You know, you could have they're actually, you move them, you sort them, and you move them from tank to tank, and so on whole, you're by the end of the production cycle, you've switched out the water one time. Yeah.
So you said most of the embedded energy comes from transportation.
Yeah.
Does that mean a RAS system will have, in New Haven side, would have less embedded energy than shipping while it's out in Alaska?
Oh. Because 94%, I mean, of course it makes, are we talking frozen product or fresh product? Are we talking, you know, what distance are we traveling? What's, you know, where's it starting from? Where's it ending up? All of these things come into the mix. But the bottom line is the vast majority of embedded energy in any fish product is in the transportation, regardless of all of those things. And so if you are going to bring the production site alongside the consumption site, you're removing the vast amount of embedded energy. Even though your production system may have a nominal increase in energy, when we start looking at the cumulative, again, right, cumulative, the math is absolute. Yeah?
Do you have a question, or?
Yeah, sure.
So I have two small questions. And one, with regular farm salmon, there's often a problem with like the chemical makeup of the fish that they can put in dyes.
Yep.
Good for you and are not as good in wild salmon. Like the nutrient ranges are all off. Is that
Right.
Is that still true of RAS?
In terms of the product itself is, you know, if you don't pigment the flesh, it's going to come out a dull gray at the end. Yes.
And the nutrient range, the nutrient profile would still be the same?
It's still farm salmon. Yeah. And in fact, as you know, well, actually, I don't want to give it away, but I mean, the feed, I mean, it's still a farm salmon in every way, except possibly that it has been grown in as optimal an environment as is possible, and if that conveys into either a nutrient or flavor profile change, it will do so in a positive way. But I wouldn't expect there to be a significant alteration in either. Okay, so that's what we're talking about. So if we moved all production, current production, let's just play God for a minute, and we're going to move all current production of salmon currently in conventional net pens, we're going to put them into a RAS system. Right? And we capped impacts at what Val estimated at for the 2012 sort of cumulative impacts of farm salmon. The question then becomes, how much more salmon might we be able to produce while capping impacts at current levels? That make sense? Right. Essentially, we can double production. So there aren't a whole lot of these systems out there yet. There are a number in British Columbia. There are a number being built or planned in the U.S. There are some in Europe. China's looking at this big time. This slide is actually out of date with regard to China already. No, so this is definitely where the industry is heading. The interesting thing from my point of view is that it removes the vast majority of excuses for why the issues are the way they are with farm salmon. It's going to be very interesting to push politicians and bureaucrats who have built up a certain amount of political momentum in explaining away escapes, sea lice, diseases, organic pollution, inorganic pollution, et cetera, as various forms of the cost of doing business sort of argument. Right? This is clearly no longer the cost of doing business. There are ways of doing business that remove all of these things and potentially improve. Yeah. You guys decide, whichever.
Given how ideal the scenario is as you presented it, is the reason why it's not more widely adopted now because it is a newer technology?
Yeah. There is huge resistance within the established aquaculture or the salmon farming community to do this. Marine Harvest is playing with one R&D farm only because I think it has to be able to point to it and say, look, we're trying this out. All of this, though, all of these farms listed here are being bankrolled by venture capitalists who are trying to achieve a political end as well as a financial end. Yeah.
Yeah, I was going to ask about the actual economics of how does it cost compared to the traditional farm system?
The biggest, I don't want to speak for this because it is, obviously a little bit more complicated than I've laid it out. The biggest determinant, though, of your financial efficacy is the cost of your electricity. So if you locate your operation on the grid where electricity is a reasonable price, that is going to change your bottom line dramatically. That is the biggest. That's the biggest determinant of your competitive power against your competitors in the marketplace, which are conventional net pens. The one thing, it's not completely rosy, right? These are still carnivorous animals. And as we saw in the assessments, the feed issue, right, is very little difference between RAS and, there's very little difference among all of these systems. There's modest increase in your feed conversion ratio or your how much fish you got to put in to get your fish out because the system is optimized, but it's a modest increase. And so when we start talking about, we could double our production, right, of farm salmon, this ignores one of the overriding most important issues, which is the reliance on these marine organisms to actually drive your production. And I just never get sick of this slide. I hope you don't. That when we look at the top 10 fisheries in the world, right, by weight, only 3 of them are fisheries that we actually directly consume the products of. The rest go to reduction fisheries, right, for feeding things like farm salmon and shrimp and chickens, etc. So, aquaculture currently consumes half of the fish meal produced out of these fisheries and others, and 80% of the fish oil. Now, I understand, next up in this series is this idea where we're going to take GM yeast, right, and produce omega-3 oils to feed to salmon. It's a good idea. It'll be interesting to see how this all plays out. At the same time, though, we have AquaBounty, who's about to get FDA approval for their genetically modified salmon, which, as those 2 fish up there are siblings. One is genetically modified, one's not. You can probably tell who's who. Fed the same diet, etc. And so there's been huge pushback on the GM salmon and the fact that this is about to become ready for human consumption in the U.S. and then by virtue Canada and probably the U.K. too. And I don't see the same kinds of things, the kind of rebuttals going on for this product here. In fact, maybe it's because I live in BC, I don't know, but to me, salmon is 5% flesh and fins. It's 95% rivers, estuaries, and oceans. And I think it's about time we start asking, when is a salmon no longer a salmon? Think of the trajectory of this story. We started out with wild salmon fisheries, particularly in Atlantic salmon, or in North Atlantic, which collapsed. And in response to that diminishing, before they collapsed, we had the advent of commercial salmon farming to try and take the pressure off of wild stocks. So the story goes. And that industry increased and improved and found efficiencies and grew even more and grew even more, grew even more, to the point when we actually started eating more and more and more salmon. The Atlantic salmon stocks, and to a certain extent the Pacific salmon stocks too, continued to collapse. We haven't kept our salmon consumption consistent and just traded farmed for wild. We continue to eat the wild, we're just eating more and more farmed. So now, farm salmon has generated all these issues, diseases and parasites and organic pollution and escapes and all of these things. So now we've got this technology, we're going to move them into these land-based pens, and it's going to create panacea. Now we can double our production of salmon. Now we can eat more and more salmon. And I'm thinking, what's the question we're trying to answer here? Or is it the fact that everybody in the world has to eat salmon? Is that the problem? I think we've lost track of what is the issue we're trying to solve. Right? And so and I don't want, and I'm not trying to set up your guest from Chile or DuPont. But I think it's worth stepping back a minute and asking, what is it that we're actually trying to do? Because if it's about generating revenue, then absolutely, you will make more money converting anchoveta into salmon, right? You will feed far fewer people by doing that. And you can even start feeding them little yeast pills, right? That's all fine and dandy because you will make money. And there's nothing wrong with that. But let's be clear about what our objectives are. And that's why I would encourage you to step back and kind of consider these larger scale issues and problems and opportunities. So with that, I'll end and take any more questions if there are any. Thank you. Yeah.
So what in your experience have been the demand drivers percent? Has it just been supply that people are just going to be set up?
Well, that's a really interesting question. I think, in the early days, the farm salmon